Hello, I am going to be going over homework number 6 for the EEDG 6370 class offered at UTD in the fall of 2024. And first, we are going to start with creating a cyber workbench project after creating the workspace just now. So, for this project, we're going to set the clock frequency to be 50 megahertz. We're going to select FPGA. It's going to be in Cyclone 5. It's going to have a speed grid of -6. The device is going to be a 5C SEMA5. Package is going to be the FC31. And we're using Cortis 2. And these are the packages. I believe we get rid of this one. Apply. We'll just hit OK. Now we're going to add a source. And for this, we are using this as a source file. So now that we've added this source file, we are going to parse it. So I'm just going to hit this, hit reanalyze, because I should hit analyze. And there were no issues. So now what I'm going to do is I'm going to generate constraints. And we'll put this up to 10. Now the constraints that were generated, you can see the F count one right here. And you can see the flib file right here. And now we're going to synthesize this. And now that we've synthesized it, we have this report right here, and you can see things like latency, clock period, critical path. Down here you can see the LUTs and registers. And down here you can see the functional units. You can see that there's 3 of the 12-bit adders and 4 of the 8-bit adders. And if we want to see a schematic for this, all we have to do is go down here to the simulation results and hit the data path. And it will bring up a drawing of what the circuit looks like. And also, what you might want to check out is the signal table, where it'll show you all these steps that it goes through. Also, something that you can do if you go to the synthesis options, if you go to the information and have it output a data flow graph, let's apply that, and then let's resynthesize this. And it'll come up with this, where you can just see how it kind of flows through, how it so this input goes to this adder right here, which goes to that adder, so on. So now if we want to compile this with Cortis into RTL, what we can do is go here and generate the script. This should all be left the same. I believe all this should just be left the same, and we just hit execute. It'll make a script for generating the RTL, and you can see that right here. And over here, what we can do is we can just do logic synthesis. We'll do it through the GUI. It might take a while for it to pull up, so I'll show you in a minute. So now that Cortis Prime has been opened, what we can see right here is the results of the synthesis. You can see that it uses 25 ALMs. It uses 43 ALUTs. It uses 66 registers. And there are 18 pins. So now we're going to go into simulations. And what we're going to do is here, we're going to make a new simulation scenario. And for the first one, we'll do behavioral. It'll just be the C++ version. And we'll be calling this AVE8 underscore software. And that's the source file. And hit OK. And here we will select a few options for the simulation. So here under build, what we have to do is we have to add C as a preprocessor option or definition. We'll hit plus to add that, and then we'll apply, and we will generate the makefile. And since the build doesn't seem to be working at the moment, we'll have to go over here to the console and run it. And now this is looking to get. So now we're going to also do a cycle accurate simulation. We'll do cycle accurate. We'll do system C. We'll call this AVE8 underscore cycle. Now we need to do a few things. So we need to compare the output value. We need to dump to a VCD file. We need to take in as hexadecimal. We use every cycle. Everything else should be the same. Apply, let's generate the test bench. Also generate the makefile. So now we'll go into the AVE8 underscore cycle. Now I will execute the makefile and run the software. And what you can see right here is that the outputs were matched. It only ran for 23 cycles, but if we go and add any like another input, you'll see that it will match 5 on the next cycle. So now that I have the VCD file open, you can see right here that it takes an input of 2, 5, 7, and so on, and what it returns is a 1, 2, 4, blah blah blah, all the way up until it gives you 7 right here. This says 10 right here. That's because it not using correct radix. It should be set that to unsigned. Set this to unsigned. So you can see that it goes 8, 7, 15, 16, 7, and if we had to go for one more cycle, what it would show is a 5. And now we will show you one more test bench, so we can generate an RTL test bench. RTL. We would use model sim. We would write to an input output file every cycle. We would take from a pattern file and we would set this to generate random data, and we would use decimal, and that is it. So let me apply that and hit test bench. But even though we can set up this test bench, it is not properly running right now. I believe the model sim software is not installed, so it won't actually simulate properly. So moving forward, we'll look at the synthesis graph. So if you go to the AV8, the blue folder, the light blue folder, what you can go over here is go to the synthesis results and hit synthesis graph, and it will show you the different synthesis results that has created so far. So we need to change this value to manual, and then change the F count, set that to 2 and this one to 1, apply, we'll resynthesize, and then we will look at the graph again. And what you can see right here is when we reduce the functional units, it greatly increases the lookup tables and it increases the latency. And we'll do one more where we will use the minimum amount. So we can put the 8-bit adders, and let's resynthesize that. And then what you can see right here is that when you go down to just one functional unit, it actually reduces the lookup tables, but it more than doubles the latency. And what we will also look at right here is when we only have one functional unit, what that looks like. Here, on the circuit. And you can see that this circuit is a lot different than the original circuit that was generated. And then also comparing this through the signal table. This is very different. See, it has a lot more stages. And so now we're looking at the RTL code that was generated, and then I modified it to take user input data and drive that out to the average number out to a 7-segment display. And what I could have done is I could have set the clock up to be, like I could have set up a wrapper that would send a clock signal every time the button is pressed, and then that would basically accomplish what we needed. But instead of building a wrapper, I decided to instead just modify the code. So I have an input data wire, a new data wire, some hex display outputs, the clock, the reset, and then some LEDs. So here I define some wires and registers, and then I assign the LED to output the input data, output this pause edge signal and the reset signal. And then right here, these are all generated by Cyber Workbench, and then these are wires that are used to drive the 7-segment display. And right here you can see I set the reset to be not the reset N, and then I set N0 to be the data register. And then right here I have an always block that uses the clock and the reset N. And then if not a reset N, then it resets everything down to 0. Else, if the positive edge signal is asserted, then it will take the next data, or else it keeps whatever data is already in the data register. And then if the new data signal is high, which means the button is not being pressed, then the debounce is set to 0. Otherwise, the debounce kind of acts as a shift register, and then once 6 is high and 7 is low, then the positive edge signal is asserted. And then right here, there's this always block that drives the 7-segment display. So this is the first number. This is the second number for the tens place. And then there's the hundreds place number right here. And all the other hex bits are never going to be anything. So I just turn those off. And then right here you can see the instances of different adder modules. And right here you can see some assign statements. This is all generated by Cyber Workbench. And then, so a lot of this right here is created by Cyber Workbench. It's basically the shift register and the return output. So I didn't modify the return, but the shift register, I added that it has to be a shift on the positive edge signal, and otherwise it retains its value. Like I said before, I could have avoided this by just having the positive edge signal kind of act as like a clock pulse, but I did not go with that. And then right here, this is all generated by Cyber Workbench, and then these are the different modules generated by Cyber Workbench. And so also we have this SDC file, which just names the clock, and then derives the PLLs and clock uncertainty. And then in this QSF file, we have all these pin assignments for the clock, reset, new data, end data, the hex displays, and the LEDs. And so now I'm going to compile this, and then I'll show you programming and putting it on the board. So now the RTL has been generated, and let's get this on the board. So let me just load the newly generated SOF, and then put that on the board. And so now I'm going to cut over to a video of it working, and I'll be right back. So here you can see the FPGA board, and so right now it's not putting anything in, so the average will stay at 0. And if we set this to, let's do 1, 2, 4, 8, 16, and put it in four times, that should be 8. 1, 2, 3, 4. And then if I hit this 4 more times, it should go to 16. And then let's turn that off. And let's put in 128. And hit this 8 times. And this should go to 128. And then let's just do like 255. Max it out. And this should go to 255 after I hit this 8 times. 1, 2, 3, 4, 5, 6, 7, 8, 255. And then let's set this back down to 0. So after 4 times, this should go down to 128. 127. Close enough. And then let me hit that 4 more times. And if you actually do the math on that, I mean, yes, it should go to 127 because it's not, because it's truncating, and it's not going to round up. But if I do 128. And then I do 0, this should go down to 64 after 4 times. And then it should go down to 32 after 2 times. And it should go down to 16. And then it should go down to, I believe, 0 now. So you can see that it works as intended. Thank you. Okay, so looking back at the requirements, I actually realized that we're supposed to make the changes with C code. So what I did is in the C code, um, I modified it. So now I have some unsigned characters right here that allow the 7 segment displays to be to show the numbers properly. And then I have this debounce integer, and I move the out v outside of the process. And then I added a boolean button input, and then these are all these are character pointers that allow me to set the 7 segment display. And so those will act as outputs, and I got rid of the original output. So I changed it so there's only the sum and the I being declared as local variables. If the button is not asserted, then the debounce will count up to 255. Otherwise, it stays at 0. And once it hits 254, then it will shift in the new data and add them all up, and then set the output v to the sum divided by 8. Otherwise, it just holds the value. And right here, it assigns the 7 segment displays. And like in the other implementation, you can see that these 7 segment displays are never going to change. And then these ones are all set depending on. So it in this implementation, it will display zeros instead of a blank 7 segment display. But this is how I calculate. So I do output v divided or modulo 10, output v modulo 100 divided by 10, and then output v divided by 100. And that should give me the proper 7 segment outputs to the 7 segment displays. And that's the changes in the C code. So I compiled this, and then I copied it over to my Windows, and then you can see in here. So this is the Verilog file output. The only things I changed is I added the _e because I'm using this in the same project as the other one, and I didn't want to delete the other file. And for the reset, I changed it so it's not reset here and here. And then in the QSF file, I uncommented the previous definitions for the pin assignments. And I reassigned them down here. So I changed the reset. I changed this to say button. I changed these ones to say N0 instead of the N data. The hex was changed to seg right here. And then I had to change it so like from 0 it went to 7 and blah blah blah. So and then 7 went to, or 6 went to 1 for all the hex displays. So those will show properly. And then I just assigned the excess hex displays to the LED pins because I didn't want them to just hang out, and I didn't want to remove them from the code. And then I programmed the device, and now I will show you a video of that working. So this is the implementation with the C code. You can see the difference really right here and down in the LEDs, because the LEDs aren't showing like the input like before, and the hex displays show 000 instead of being these two being blank. And to show that it works, we'll start with 128. We'll just shift that in 4 times for 64, and then 4 more times for 128. Then let's make this. Make this go down to 64. So I'll shift this in 8 times. And you can see that it's properly cycling through the different numbers. And then let's just make this 16 now. So you can see that it's working properly. And just to show you, I will do lastly 255. And so you can see it's working properly with the C code. So now everything has been shown to work properly. Thank you for watching.